Let's talk about bounds for sets. I find it easiest to just start talking about distances and bounds in Rn, even if our immediate interest is in one dimension, in the real line. So here, we use Euclidean length with the standard notion of length for a vector, also called the norm, or the magnitude of a vector. At times, there are other notions of distance, but this is the standard one, which we will use unless specified otherwise. The length of a vector is denoted using either single or double bars. And for my undergraduates who are used to seeing special notation for vectors, like having an arrow symbol on top or boldface fonts or something, you won't see those here. You'll have to pay attention and infer from context when we're talking about a vector as distinct from a scalar. If your interest is in the real line, then length just reduces to ordinary absolute value. In Rn, for any n, all vectors satisfy the triangle inequality shown here. This is an essential feature of any true notion of distance, part of the definition of distance. So even if we replace the Euclidean norm by another notion of distance, we will still have to assume this triangle inequality. The triangle inequality certainly holds in R1, but there the name would be a puzzlement without reference to this larger perspective. I haven't said anything here about a proof of the triangle inequality. And admittedly, the proof in one dimension is much easier, because there you just check the validity in separate cases, depending when the numbers x, y, and x plus y are positive or negative, or zero. The proof in two or more dimensions takes a little more work, but I won't worry about that here. Actually, the length of x plus y is bounded both above and below, as shown. The upper bound is the first form of the triangle inequality, the standard way to state the theorem. The lower bound shown here is often useful, so it's worth spending just a moment to derive it. And I'll derive it from the original form of the triangle inequality as follows. The absolute value of x has this upper bound using the original form of the triangle inequality. Now move the last term, absolute value of y, to the left-hand side. And if we exchange the x and y, exactly the same inequality must hold. That's by symmetry, meaning we just interchange x and y. If they're arbitrary, the same argument has to hold. Now look at the left-hand sides of the last two lines. They are practically the same, except that one is the negative of the other. Throw away whichever one is negative and keep the one that's positive, since the other one isn't telling you anything that you don't already know. And the other one, the one that you care about, is written in this form. That's our proof. I've started using the terminology of bounds already in my video. I hope that the term is clear, and in any case, I'm going to clarify it at a later point. I do point out that we use the word bound both as a noun and as a verb. In the top statement, we have an upper and a lower bound for the norm of x plus y. The upper bound shown on the right, the lower bound on the left. So there I was using the word bound as a noun, and as a verb we can say we have bounded the norm of x plus y, both above and below. Be forewarned that inequalities will be a big part of our course, as with any analysis course. My experience is that undergraduate students typically are less acquainted, familiar, experienced dealing with inequalities than with equalities. And it's a feature of analysis that there are a lot more inequalities here than in algebra courses. Now, vectors in Rn often used to represent points or positions. The distance between these two positions is the norm of their difference. Whenever you see an expression like norm or absolute value of y minus x, you should instinctively interpret this as the distance between x and y. If your mind doesn't immediately jump to that association, you need to train yourself to have this instinctive reaction. So this is another form of the triangle inequality equivalent to the first, but perhaps with a slightly different emphasis, because now I'm interpreting x, y, and z as points rather than arrows. But here is the proof of this form of the triangle inequality. You'll need to be able to fluidly do these kind of manipulations so that you can use the triangle inequality as needed. Here now is a little geometry, and I'm showing you pictures in 2 dimensions for starters, even though something similar works in any number of dimensions. A circle in the real xy plane is the set of points satisfying this quadratic equation. Here AB is the center of the circle, which can be any point in the plane. R is a positive constant, which is the radius of the circle. In other words, the circle is the set of all points at distance r from the center. When we talk about the set of points at distance at most r from the center, we don't get a circle, we get a closed disk. So this is like putting a leash on our points and seeing how far they can go. If we take the set of points at distance less than r from the center, we instead get the open disk of radius r, centered at AB. In everyday usage, the words circle and disk are often used interchangeably, but in mathematics, here you see there's a big difference. The circle is just the boundary. The disk includes all the interior region. Depending on whether or not we include the boundary, we get either a closed or an open disk. All of this generalizes to Rn for any n. If A is any point, notice here that A is now a vector. The set of points at distance r from the center is a sphere of radius r. The set of points at distance at most r from the center, A, is a closed ball. The set of points at distance less than r from the center is an open ball. My picture here is not very helpful in distinguishing these 3 notions because you can't see inside. But they are 3 different notions. Again, language on the street uses the words sphere and ball interchangeably. In mathematics, they are not the same. A sphere is just the boundary. The ball includes all the interior. The ball is closed or open, depending whether or not we include the boundary. And again, we talk about spheres and balls in any dimension. If n equals 3, this is the usual notion of sphere and ball. If n equals 2, then this is the usual notion of circle and disk. So those are special cases. In our course, we care mostly about n equals 1. But once again, the intuition from higher dimensions, especially 2 and 3 dimensions, is helpful. And now, getting to the real line, we take a sphere of radius r centered at a point A. This just gives us a pair of points, right? The endpoints of an interval of radius r centered at A. The points at distance at most r, the ball, form a closed interval of radius r centered at A. The points at distance less than r from A form an open interval of radius r centered at A. It's helpful to think of closed and open intervals as just closed and open balls in one dimension. Now, a set of points S in Rn is bounded if the norm of each point in that set is at most r, for some positive constant r. Bounding a set is a way of saying it does not extend off to infinity in any direction. Just to practice, here is an easy theorem. A set is bounded if and only if it is contained in some ball. In order to make the proof go smoothly, let's introduce some notation. This notation is pretty standard, though some authors vary the notation a bit, sometimes, for example, reversing the r and the a. I will write b sub r of a for the open ball of radius r centered at A. If I put a bar on top, then I get the closed ball of radius r centered at A. Now, by definition, for a set S to be bounded, that means it is contained in some closed ball centered at the origin. The radius of the ball is just some positive constant. This already proves the statement in the forward direction. So that was painless. Just read the definition. Now let's prove the reverse direction from right to left. So suppose now S is contained in some ball. Are we assuming this to be an open or a closed ball? Well, it really doesn't matter, because an open ball is already contained in a closed ball, so we can definitely say that S, by our assumption, is contained in the closed ball of radius r centered at a point A. By definition, every point of our set S has distance at most r from the center A. So by the triangle inequality, the norm of x is at most r plus the norm of A. So S is contained in the closed ball of radius r plus absolute value of A, or norm of A, centered at the origin. That's all there is to our proof. In the last step, we found a closed ball containing S, so we certainly showed that S is bounded. If it should so happen that you need an open ball containing S, no problem, just choose a slightly larger radius. But in this case, we did everything that was asked of us, so we're happy. Now in one dimension, for subsets of the real line, a slightly different question arises, because here we can talk about an upper and a lower bound for a set S. So in addition to coming up with one number as a bound, we can find two different numbers, one on each side. So we say capital M is an upper bound for the set S if every element of S is less than or equal to M. And lowercase m is a lower bound for S if each element of that set is greater than or equal to little m. For example, let S be the set of social security numbers of students in our class. Then 999,999,999 is an upper bound for that set, and 0 is a lower bound. Of course, we might be able to do better than that, but we could certainly do worse. Every number bigger than 999,999,999 is also an upper bound, and every negative number is also a lower bound for the set S. As a second example, the set of positive real numbers has no upper bound. We say it's not bounded above, but it is bounded below. The lower bounds for the set of positive numbers are precisely the numbers less than or equal to 0. So if we're looking for lower bounds for the positive numbers, then the greatest lower bound is the number 0. Looking for upper and lower bounds for a set is something we can't really speak about in higher dimensions. In the real line, it is very important. We often want to ask for the best upper or lower bound that we can get. Another example, let A be the set of all rational numbers whose square is less than 2. Here is another way to think of this set. Take the rational numbers intersect this particular open interval. This set has an upper bound of square root of 2, and in fact, this is the best upper bound. It's the least upper bound. The set A is also bounded below. We can take minus square root of 2 as a lower bound for the set A. This is again the best you can do. Minus square root of 2 is the greatest lower bound. Now here are the definitions. It's really plain English at this point. For a set S, we say capital M is the least upper bound if M is an upper bound, first of all, and secondly, it is less than or equal to any upper bound. For some sets, there might not be an upper bound, let alone a least upper bound. But we can say if capital M is a least upper bound, then it's the only one. There can only be one, if any, least upper bound. That's why we speak of the least upper bound rather than just a least upper bound. There can, however, be many upper bounds. Similarly, we define the greatest lower bound, which again may or may not exist, but if it does, it's unique. These notions are extremely important because they get at one of the most important ways of defining properties of the real number system and saying what's distinctive about the reals. Here, we summarize that important property. Take any subset S of the reals. If S has an upper bound, then it has a least upper bound. If S has lower bound, then it has a greatest lower bound. The property of the real numbers that we need to make this work, make this theorem hold, is the property we call completeness. Note that the rational numbers do not have this property. For example, let A be the set of solutions of A squared less than 2. Then A is bounded above, for example, 2 is an upper bound. Is there a least upper bound? Well, not in the rational numbers. No, there's not. So the rational number system is not what we call complete. But in the real number system, there is a least upper bound, which we call square root of 2. Now on my slide, I've called this statement a theorem. So where is the proof? Can I actually provide a proof? Well, that depends on your point of view. One point of view is that we take the real numbers and all its properties for granted. In that view, the assertion of this theorem is automatic or axiomatic. We just assume it. And we will favor that approach because it gets us up and moving much faster. If you prefer the other approach, you should realize what it is you're asking. In order to actually prove something like this, prove a theorem, you need presumably to be proving it from something more fundamental. That would mean presumably from a foundation of the real numbers grounded in the rational numbers. And you could talk about how the real numbers could then be constructed and all its basic properties proved from what you know about the rationals, which is certainly a feasible task, but we're not taking time to go through those details all here. Let me say, one might also want to question the existence and properties of the rational numbers at that point. Does one then take the rationals for granted, or does one construct the rationals from the integers and then prove all of its properties? How much are you willing to take for granted? If you're a skeptic at heart, good for you. You want to see the foundations exposed for what they are, nevertheless, you have to start somewhere with some underlying assumptions, typically the assumptions that come from the axiom of ZFC set theory. For now, though, I'll take the statement of this theorem for granted since it gets us to work sooner and up and doing the business of analysis. So rather than refer to it as a theorem, let's refer to it as the least upper bound property for the real numbers, just something that we assume. By the way, if we have statement 1, we automatically have statement 2. Because for any set S, replacing each element by its negative switches the problem left to right. So upper bounds give us lower bounds. Least upper bounds give us greatest lower bounds. So if one exists, so does the other. Now the least upper bound for a set S, if it exists, is called the supremum of the set. We abbreviate the supremum of S by the sup of S. Also, the greatest lower bound of S is called the infimum of the set, and it's abbreviated as the inf of S. These are words from Latin, should remind us of other Latin words that we use like maximum and minimum and extremum. In fact, the case of a finite set, the supremum is just the maximum element of that set. The infimum would also be the minimum. But for an infinite set S, the concept of suprema and infima is really more subtle than maxima and minima because the supremum and infimum can exist even when the maximum and minimum don't. So read these statements carefully, make sure you understand them. If a set S is bounded above, it has a least upper bound M, which is the supremum. In the case of upper bounds, they form an interval from capital M to infinity as shown here, and a similar statement for the infimum. As well as bounding sets, we can talk about bounding functions. Given a real valued function f, we say f is bounded above if its set of values as a subset of the reals is bounded above. So this is not a new concept, just another way of applying the terminology. In this case, we talk about the supremum of the function, which is the supremum of its set of values. Similarly, we talk about a function being bounded below if its set of values is bounded below. In this case, f has a greatest lower bound called its infimum. The function is simply bounded if its set of values is bounded. But this is the same thing as being bounded both above and below, just like for sets, by the way. For example, the sine function is bounded between plus and minus 1. Its supremum is 1, and its infimum is minus 1.